because this is the makeup, and actually this is the extra online lessons. So I will take a few minutes to return to the Poisson distributions. Okay, some of you, if you already done these sessions during the in class, so it will be okay. So it will be the chance for you to review this. Okay, and then after the Poissons, we continue with the order distributions. Okay. Okay, so let's talk about the Poisson distributions. To define the Poisson distributions, now we have looked on the example 6. Suppose that now we're interested in our communication system. And in this system, we transmit n bits. Okay. And if S denotes the number of errors in n transmitted bit, and suppose that the property of getting error for one bit is a constant p, and the errors are independent between bits. So according to our knowledge about the binomial distributions, we know that if S indicates the number of errors among n transmitted bits, hence S must follow the binomial distributions. Okay, so using the formula of binomial distributions, now we have the probability of S equals to K equals to C n K P power K 1 minus P power n minus K. Okay. Moreover, if we consider the average number of bits E of S equals to NP and denoted by the constant lambda, then because lambda equals to NP, hence easily we can write P equals to lambda over N. Okay, so plug into the formula of binomial distributions. So we write the probability of S equals to K equals to C n K lambda over N power K 1 minus lambda over N power N minus K. Okay. So in reality, we will transmit a large number of N. It means that mathematically, we are considering N is approaching infinity. Okay. N is larger and larger. So it means N approach infinity. Moreover, it's also convenient. It's also meaningful to consider the average number of the error, always the constant. This is the lambda. It means that if we increase the number of transmitted bits, then the probability of getting error for one bit will be smaller and smaller, such that when n is large, p is small, and then their product always gives as the constant lambda. Okay, so it means that now we consider the property of S equals to K when n approach infinity and lambda is considered as a constant. In this case, we can prove that this limit will be the constant values. Its values is e power minus lambda power k over the factor of k. You can prove this by yourself. You can take the limit of this term, calculus 1 knowledge. Take the limit of this term, surely it's conversion to this term. Okay, and now because n in the binomial distributions is from 0, 1, 2 until n, and n approach infinity, of course k will be 0, 1 to n. It's up to infinity. We are considering all of the positive integers. Okay, and you can easily prove that the sum of this term for any positive values of k will be 1. Okay, what does mean? What is the meaning of this example? This example tells us that the limiting distributions of the binomials will be unordered distributions, which is given by this probability. Okay, it means that we considering the limit of the binomial distribution. The binomial distributions will conversion to unordered distributions. When n is enough large and p is enough small. Okay, and in this case, we define the limiting distributions of the Poisson of the binomial distributions is the Poisson distributions. Okay, we derive to the Poisson distributions basing on the limiting distributions of the binomial distributions. Okay, so officially we define a Poisson distributions. We define the Poisson distributions will be the random variable S denoted by P lambda, where lambda is the unique parameter. Is the unique parameter in these distributions. It describes the number of events that occur within the unique length or unit space. Okay, where lambda is the average number per unit. Okay, so you can see that because the Poisson distributions is derived from the binomial distributions, and the binomial distributions describes the number of events among the sample of n trials, and then we take n approach infinity. Hence, the Poisson random variable also describes the number of events. But now it's not limited in a sample of n anymore. Now, the Poisson random variables describes the number of events, but relating to a unit. This unit can be the unit of length or the unit of space. Okay. For example, it can be 1 hour, it can be 1 year, it can be 2 years, it can be 1 day. This is the unit of time. Or it can be the unit of space. For example, it can be 1 city, 1 post office, 1 town, 1 house, 1 city, 1 millimeter, 1 millimeter square, and so on. Okay, as long as that you want to describe the number of events that occur within the unit length, okay, according to a unit, okay, and lambda indicates the average number of events per unit. Hence, the Poisson random variable S can be the suitable choice. Okay. For example, here, if we care about the number of misprints on the page of the book. So in this example, what is the event? The event will be the misprint. We're interested in the misprint. Okay. And the unit we're considering will be 1 page of the book. Okay. We are considering a page of the book. Or the number of people in the community who are at least 100 years old. So the event will be 1 person who are at least 100 years old. And according to the unit we are considering will be a community. Okay, so this also modeled by the Poisson distributions. Or the number of people entering the post office on a given day. Hence, the event we are considering will be a person entering the post office. And the unit will be on a given day. Okay. So as we already showed from example 6, we see that the probability match functions of S will be Fk equals to the probability of S equals to K. It's equals to E power minus lambda power K over the factor of K. Okay, K equals to 0, 1, 2, 3, and so on. Okay. And here, in this example, the mean values exactly equals to the variance value and equals to the unique parameter lambda. Okay. So when you work with the Poisson distributions, it's really important to pay attention for the unit we're using. Because lambda indicates the average number of events per unit. Of course, if you use different units, then you have different parameter lambda. Okay, so you need to recalculate lambda if you use different units. Okay, so later when you work with the data in statistic chapters, you will see that in case if you calculate the mean and the variance of the data set, and you see that if they are quite different, then we confirm that the Poisson distributions will be not the suitable choice, because the Poisson distributions will be defined for the mean exactly equals to the variance. So in reality, if you see that any data and the mean is quite different to the variance, so you show this is the signal to see that you shouldn't use the Poisson distributions in this case. Okay. Next, we have two important properties of the Poisson distributions. The first one will be the first properties allow you to take the sum of n independent Poisson random variables. It said that if xi follow Poisson distributions with lambda I, and n and of course lambda I has the same unit. If they don't have the same unit, you need to change the unit to be the same. Okay, and if xi are independent, hence you can take the sum of n independent Poisson distributions. It still be the Poisson distributions with the new parameter lambda equals to the sum of lambda I. Okay. If the first one allows you to take the sum of n independent Poisson distributions, then in the second properties, it allows you to split one Poisson distributions into several Poisson distributions. Okay. Here, it said that if we consider Z is the Poisson distributions with the mean is mu, and the outcomes or the events, each of them will be independently classified into one of F groups. Then if Zk indicates the number of events according to group K, hence Zk also follow the Poisson distributions with the mean, the new mean equals to the probability of belong to group K multiply the probability multiply the mean of Z. Moreover, Z1 from Zm also are independent. This means that you are splitting the Poisson distribution Z into m independent Poisson distributions. Okay, and of course they have the same unit. Okay. Okay, let's see this example. Okay, so suppose that we have set follow Poisson distribution with parameter. Wait. So suppose that we have set indicates the number of people or customer entering post office per day. Okay, so the unit will be 1 day. And suppose that we know that follow Poisson distribution with lambda equals to 10. It means that averagely there are 10 people entering the post office per day. Okay. Now we are interested in splitting Z. We are interested in splitting or classify people entering this post office into two groups. Group one will be the people entering the post office, and they are the females. And the second will be the males people entering the post office. Okay. Hence, we have Z1 indicates the number of female entering the post office per day. The unit still be per day. Okay. And then group 2, Z2 will be the number of males entering this post office per day. Okay. So you see that here, each person entering the post office, we classify them belong to only group 1 or group 2, males or females. Hence, here we have 2 groups. And at beginning, actually, we don't know the distributions of Z1 and Z2. But with the properties of the Poissons, we know that Z1 also follow Poisson distribution with the new parameter lambda 1 equals to P1 multiplied parameter lambda. And suppose that the historic data show us that there are 70% of females entering the post office and only 30% of males entering the post office. Hence, we can know that Z1 will follow Poisson distribution with lambda equals to 0.7 multiplied 10, so we have 7. And similarly, Z2 also follow Poisson distribution with lambda 2 equals to P2 lambda. Hence, we have Z2 follow Poisson distribution with parameter 3. Moreover, Z1 also independent to Z2. Okay, this really meaningful properties of the Poisson distributions. Starting from beginning, you only have one Poisson distributions, but now you're splitting into 2 independent Poisson distributions. Okay, any questions? Okay, during the class time, if you have any questions, you can raise your hand or you can turn on your microphone. Okay. Okay, so now a little bit practice. Wait a bit. Okay. 3 minutes for you. Answer for the given example. Question 1, 2, and 3. Then please show me your answer in the chat box. Okay. 3 minutes. Then please show me your answer in the chat box. It's time for you. Anyone has done? I'm waiting for your answers. Please show me in the chat box. Okay. Question 1. What's your answers? Here we have more than 80 students in the class, but I haven't yet received any answer from you. Can you do it? Okay, I received the first answer from Yuchen. How about the other students? It's time for your practicing. Students, maybe it's too small for you. Okay, some more. Okay. Now return to the whiteboard. Questions. Okay. A customer service can receive the customer feedbacks via emails or phone calls. It's assumed that in an hour, the number of calls to the service hotline is the Poisson random variable S with the mean is 29 calls per hour. So firstly, we denote S will be the number of calls per the unit of 1 hour. Okay, don't forget the unit. The unit always, well, when you work with the Poisson distributions, always remember to always remember to identify the unit we are using. Okay, and it's written that as follow Poisson distribution with the mean Australian is still visible too. Okay, it's written that as follow the Poisson distributions with the mean is 29, so we rewrite 29. Averagely, there are 29 calls per hour. Then what else? We also given the number of emails is following the Poisson distributions. We have Y is the number of mails per hour. Y also follow Poisson distribution with lambda equals to 49. Okay, find the property that this customer service receive 22 calls in an hour. So we have question A. Find the probability that the service receive 28 calls. So we will ask 28 is x equals to 28 per 1 hour. We already have the same unit. Okay, so we have lambda 1 equals to 29, and here lambda 2 equals to 49. Okay, so the property of x equals to 22, we have the property of x equals to k equals to e power minus lambda power k over the factorial of k, so over 22, the factorial of 22. Okay, then you just calculate, you're able to get the final answer. Question B. How about question B? Find the average cost of this customer service received in 10 minutes. Here it still be the cost. The cost is mean that we're working with the random variables. Okay, and now the unit is different. Now we are using 10 minutes instead of 1 hour. Okay, hence we need to redefine the parameter lambda. We have lambda 1 now equals to 29, multiply the unit we're using. We're using 10 minutes. So 10 over 1 hour is 60. Okay, so we got the new lambda. Okay, so we want the average cost. The average cost is mean that we need E of S. As follow Poisson distributions, hence E of S exactly equals to parameter lambda, where lambda is the new one. We just change the unit. Hence E of S equals to 29 multiplied 10 over 60. Okay, so we're done. Question B. How about question C? Question C. Suppose that the number of emails and the number of calls to this service are independent random variables. Find the probability that this service channel receives 9 feedbacks in 7 minutes. Hence, we only care about the feedbacks. We don't care whether this is the emails or this is the calls. So let's just indicate the number of feedbacks. Okay, so very clearly, because one feedback, it can be emails or it can be a course. Okay, so the number of feedbacks will be the total number of emails plus the total number of calls. Okay. Moreover, because X follow Poisson distribution and Y also follow the Poisson distributions, X and Y are independent. Okay, because X independent with Y. Hence, easily we write Z follow Poisson distribution with the new lambda equals to lambda 1 plus lambda 2. Of course, using the same units. Okay, this is on the units of hour. Sorry, I forgot. Still be the units of hour. So we have said follow Poisson distribution with lambda 1 is 29, lambda 2 is 49, 29 and 49, right? Plus 49. Okay, so we have 78. So right, 78. Okay. Now, it said that we only consider in 7 minutes. So have the new lambda equals to 78 multiply the unit is 7 over 60. Okay. The property that the service channel receive 9 feedbacks. So the probability of Z equals to 9 equals to e power minus lambda, so minus 78 multiply 7 over 60. Lambda power k 78 multiply 7 over 60 power k, so power 9 over all of them over the factorial of 9. Okay, hence you should get a final answer. Okay, this is the multiplication. Okay, is this okay, everyone? Is it clear for you? Everyone, is it clear for you? It's okay. Can I ask where we have 78? Okay. Z follow Poisson distributions with the new lambda equals to lambda 1 plus lambda 2. Lambda 1 is 28 and lambda 2 is 49. Okay, so I have 78. Is it okay? Võ Xuân Hải. Using the first property of the Poisson distributions, the sum of n independent Poisson distributions is still be the Poisson distributions. Of course, using the same unit. With the new lambda equals to the sum of n lambda I. Okay. Is it okay? Xuân Hải. 29 and 46. In the question, is 29 and 49, is it right? Oh, 46, okay, sorry. Okay, so I'm wrong here. Okay, it's okay, this is 46, okay. But I'm writing on the board is 49, okay. But about the idea for the solutions. All of you, do you understand? This is the applications of the Poissons. Okay, that's all right. Okay. Okay, so return to the slides. Okay. Okay, the next property of the Poisson distributions is the approximations between the Poisson and the binomial. And actually, we already talked about this at the beginning of these sessions. When we derive the Poisson distributions, remember that we started from the binomial distributions. We have defined the Poisson distributions as the limiting distributions of the binomial. Sorry. Okay. So here I just illustrate this idea. We said that if n is not large and p is not small, hence the binomial distributions will be approximately equals to the Poisson distributions with the new lambda equals to n multiplied p. Okay. So to illustrate from this property, look at this figure. In this figure, I try to fix one Poisson distributions with lambda equals to 5. Can you see? Lambda equals to 5. And then I constructed a sequence of some binomial distributions with different values of n and p. Then we show that the binomial distributions will converge to the Poisson distributions. Okay. Remember that when we talk about the approximations between Poisson and binomial, it doesn't mean that every Poisson distributions can be approximated well by the Poisson distributions. No, it's not true. Okay, it's only true in case that the Poisson, in case that the binomial distributions has the large number of sample size. It means that n is very large and p is very small, such that p in the Poisson distributions, lambda is exactly equals to n multiplied p. Okay, it must be true within this constraint. Okay, so here, the first step, I constructed the Poisson distributions with lambda equals to 5. Okay, here this shows, in this figure, it shows the property match functions of the Poisson distributions basing on the vertical black bars. Okay, and then firstly consider the binomial distributions with n equals to 10. If n equals to 10, then p equals to lambda over n, which is 5 over 10. Okay, and its property match functions is illustrated by the small red circles. Look at the small red circles on the plot. You can see that it stays so far comparing to the vertical black bars. Especially look at the positions s equals to 5. Okay. When s equals to 5, the property of s equals to 5 calculated by the Poisson distributions is around 0.17. Okay, look at the black bars. Whereas when we calculate the property of s equals to 5 using the binomial distribution with n equals to 10, hence the red circle here indicates this probability is around 0.25. So 0.25 is much far comparing to 0.17. Hence, we see that the Poisson distributions with n equals to 10 and p equals to 5 over 10 is not enough to approximate the Poisson distributions with lambda equals to 5. Now, if we continue with the second binomial, where n equals to 20, we increase n to 20, hence p will be reduced to 5 over 20. Look at the blue circles. Now, the blue circles are better than the red circles, but it still stays far comparing to the black bars. For example, at position s equals to 5, the probability of s equals to 5 calculated by the Poisson distributions is around 0.17, but calculated by the binomial distributions with n equals to 20 is around 0.20. It's still far from 0.17. Okay. Now, lastly, if we increase n up to 1,000, and of course now p is very small, only 5 over 1,000. Hence, very easy. You can see that very clearly. We can see that the green circles, they're almost identical. They're almost identical to the black bars. It implies that the binomial distributions now approximately equals to the Poisson distributions. This means that now in this case, calculated the property of s equals to k using the binomial or using the Poissons still be similar. You get the similar results. Okay. So this example can show you that when we increase n is enough large and p is not small, then you can use the Poisson distributions with lambda equals to np to approximate for the Poisson for the binomial distributions. Okay. Why this approximations is meaningful? Why is it significant? Look at the next example. Example 8. Example H. Suppose that 1 in 5,000 light bulbs are defective. What is the probability that there are at least 3 defective light bulbs in the group of a size 10,000? So in this example, we are interested in the number of defective light bulbs among a group of 10,000. So it means that now if we denote X will be the number of defective bulbs. Okay. Hence, we are considering the sample of n equals to 1,000. And P equals to, P is the probability of getting 1 defective bulb. And this is written by 1 over 5,000. Okay. So it's very clearly that here in S we are counting the number of defective among the sample of n bulbs. So of course we have S must follow binomial distribution with n and p. Okay, S exactly follow the binomial distribution with n and p. Okay, because we counting after time. If we count about the number of events among a sample of n independent trials. This will be the binomial distributions. Okay. So if H follow binomial distributions, then the probability that we have at least 3 defective light bulbs, this means H at least 3, H greater than or equals to 3. Okay. Using the formula of binomial distributions, we have C and K. Okay. We have the probability of S equals to, we have 1 minus, we have 1 minus probability of S less than 3. If S less than 3, we have 1 minus probability of S equals to 0 minus probability of S equals to 1 minus probability of S equals to 2. Okay. Using the formula of C and K, we have 1 minus S equals to 0, so we have Q power n. So we have 4,999 over 5,000. Power n is power 10,000. Minus S equals to 1, so K equals to 1. So we have n is 10,000. P is 1 over 5,000. Power, one of this. Power n minus 1. So 9. 1, 2, 3, 4 numbers. Okay. And then what else we have? 4,999 over 5,000. Power 9,999. And one more. Oh my gosh, it's very long. So C 10,000 power 2. Again 1 over 5,000 power 9,999. 4,999 over 5,000 power what? 999. Sorry, this the first one is power 2. H and this is 2. Okay. Anyway, I just want to show you that in this case, even though we know exactly distributions of S is the binomial distribution, but you can see that it's very, very long in the calculations. It's very inconvenient. Okay, it's really inconvenient to work with very large number, 10,000, 4,999, 5,000, 1/5,000, and so on. Okay, we don't like it. Whereas, if you remember about approximations between the Poisson and the binomial, you see that now n is very large, which is 10,000, and p is very small, only 1/5,000. Hence, we can write lambda equals to np. Now, np only equals to 2. The number 2 is much more beautiful comparing to a large number, 10,000, 5,999/5,000, and so on. Okay. Now, instead of using the binomial, now we approximate the division of S. Now approximately, S is approximately follow Poisson distribution with lambda equals to 2. Okay. Hence, the property of S greater than or equals to 3 equals to 1 minus the property of S equals to 1. Property of S equals to 0, 1, or 2. Using the formula of the Poissons, we have e power minus lambda power k over the factor of k. So we take e power lambda outside. So e power minus 2. Lambda power k. So with k equals to 0, we have 1. Plus lambda power 1, we have 2. Lambda power 2, we have 4/2, and then it's 2. So very easily, we have 1 minus 5 e power minus 2. Okay. So you can see that even though this is just approximation, but using these approximations, in this case, you have very, very beautiful values. 1 minus 5 e power minus 2. It's very convenient. Okay, comparing to these solutions. And if you use your calculator, you will see that surely this number and this number, they are approximately equal to each other. Okay, and the meaning is that when you do very complicated, very long algorithms, then it simplifies equations that help you to save a lot of computational time and a lot of memories. Okay, that's the meaning of this approximation. Okay. Okay, about the Poisson distributions, do you have any questions? Do you have any related question? Everything is clear for you? Okay. Okay. Let's continue. So we have done together 3 discrete distributions. The first one is the Bernoulli trials. The second one is the binomial. And the second and the last one we just done is the Poisson distributions. Now let's move to the first continuous distributions. It's also the easiest one, the most simple one within the continuous distributions. That is the continuous uniform distributions, and denoted by the notation U A to B. If H follow the uniform distributions from A to B, H will have the property density functions and the cumulative distribution functions as given here. Look at the density functions. We have Fs equals to 1 over b minus a. S belongs to the interval from a to b. Or fs equals to 0 everywhere outside of the given interval. Okay, so look at the figure here. The density functions of the uniform random variables will stay constant between a to b and 0 outside. Okay, so what is the meaning? What is the meaning of the uniform distributions? Suppose that you are waiting for an important knowledge. Suppose that you're waiting for an important message from someone. Okay, and you have no idea about the arrival time of this message. You just know that the message may arrive between 7 a.m. to 7 p.m., for example. And you have no idea about the arrival time of this message. It can be arrived very early at beginning of the day. It can be from 7 a.m. to 8 a.m. Or it may be arrive very late at the end of the day. It can be from 6 p.m. to 7 p.m. Okay, we have no idea about the arrival time of the message. So in this case, we said that the arrival time of the message will follow the uniform distributions. So we use the uniform distributions in case that we have no idea about the probability you get or the chance you get for the values of the random variable S. We just know that it may arrive between the interval from A to B and no idea about its arrival time. So this is the continuous uniform distributions. Okay. And this properties of these distributions also can be derived from the calculations like this. Now, let's consider as follow uniform distribution between A to B like this. And consider the interval I will be the subset of A to B. Okay. Hence, the probability of S belongs to this interval. How to calculate the probability of the continuous distributions? Everyone? Chapter 2 knowledge. Calculate the probability of a continuous random variables. We consider the integral over the given interval of the density function fs/ds. Okay, do you remember? Chapter 2. Now, this is the integral over I of fs. Fs will be the density function of fs will be 1 over b minus a for any value of s belong to this interval. So we have ds. And 1 over b minus a is the constant. So easily we have 1 over b minus a. Multiply the length of the given interval. Okay. So what is the meaning of these calculations? It said that the probability of S belongs to any interval I, which is the subset of A to B. Hence, this probability only depends on the length of the given interval, because B minus A is already the constant. Okay. The probability is the chance. It means that the chance of S belongs to any interval belong to A to B. It only depends on the length of the given interval. That's the reason why I told you that when the message arrive between 7 a.m. to 7 p.m. and you have no idea about the arrival time of the message, then the message will follow the uniform distributions. It means that the message can arrive very early at the first 1 hour or very late at the last 1 hour or at the mid of the day. It still be the same. As long as that you have the length of the interval will be 1 hour then the probabilities or the chance that the arrival time of the message belong to any interval of one hour is still be the same. Okay, because the probability to belong to any interval is only depend on the length of the interval. They don't care whether the first 1 hour or the last 1 hour is still be the same, as long as that the length of the interval still be the same. Then we have the same probability. Okay, that's the meaning of the uniform distributions. Now return to the slides. Here, easily, if you use chapter 2 knowledge, you can write the mean and the variance of the uniform distributions. E of s equals to a plus b over 2, and v of s equals to b minus a squared over 12. Okay, using the integral, you're able to prove it. Now, quickly, tell me, look at example 9, tell me, what is the probability of s less than 3, everyone? Tell me quickly. Probability of s less than 3 will be everyone. What is the probability of s less than 3? It's easy. Okay, so s less than 3, it means that you are considering s between 0 to 3. Okay, the probability of s belong to the interval from 0 to 3 is equals to the length of the interval, which is 3 minus 0 over b minus a. You have 10 minus 0, so you have 3 over 10. Very easy, right? Then question B, the probability of s greater than 6. S greater than 6, you have the probability of s greater than 6 and less than 10. So from 6 to 10, you take 10 minus 6 over 10 minus 0. So we have 4 over 10. Okay. And finally, from 3 to h already belong to the interval from 0 to 10. So take h minus 3 over 10 minus 0. We have 5 over 10. Okay. Hence, calculating the property relating to the uniform distributions is very, very easy. Okay. Is it clear for all of you? Okay, all of you, you're able to find those probabilities. Any questions? Any questions? Okay. If no questions, next time for you. Practice on example 10. Few minutes for you. Focus on example 10. And then show me your answer in the chat box. Three minutes. Any answers, everyone? Answer for this example. Few more minutes. We have around 90 students in the class, but no answer now. Okay, one more minute. Okay. It's given that we have 3 slots for the shows at 9 a.m., 9:30, and 10. Once the show starts, the gate will be closed. A visitor will arrive at the gate at the time uniformly distributed between 8:30 a.m. and 10 a.m. What is the property that the visitor need to wait less than 10 minutes for a show? Okay. So first of all, of course, to find the probability, we need to know the random variables. Okay. Let S to be the arrival time, because it's already set that the arrival time of the visitor is randomly or uniformly between what? Between 8 a.m. to 10 a.m. Okay, so we will denote S be the arrival time of the visitor. Okay, because the arrival time of the visitor is between 8:30 to 10. So to transform into to model by using the random variables, we need to have the real values. It's not the time. Okay, so we need to transform the time into the real values. That's the reason why usually we will define the random variable as according to the visit time. Okay, so I will write the arrival time of the visitor started from started from age 30. Okay, so S will follow uniform distribution from 0 because started from age 30 to 10. 10 will be 9 minutes. Okay, the arrival time written in the unit of minutes. Okay, so S follow 0 to 90. Okay, here we have age 30 to 10. It means this interval is 0 to 90 minutes. And the 3 shows will be at 9. And at 9:30 and at 10. So 1 shows, 2 shows, and 3 shows. Okay, 1 slot, 2 slots, and 3 slots for a show. Okay. It said that the visitor need to wait less than 10 minutes. So the visitor need to wait less than 10 minutes. In how many cases? How many cases should we have such that the visitor need to wait less than 10 minutes? We have 3 cases, right? The visitor can arrive for the first slot, and he needs to wait less than 10 minutes if he or she arrived between age 50, okay, age 50, yeah, age 50 to 9. So from age 50 to 9, this is the interval of 10 minutes, okay? So from age 50 to age 30, we have 20, okay? So this is the property of S between 20 to 30, okay? Sorry, wait, I have a call. Okay, so similarly, the visitor can arrive for the second slot, which is around 9:20 to 9:30. Okay, so from 9:20 to 9:30, we have plus the second case property of 9:20 to 9:30. So it is S between 9:20. So from here to here 60, so 50 minutes to 60 minutes. Okay, plus the last case, the property of S between this visitor can arrive for the last shows, the last slot of the shows. Okay, so from 9:50 to 10, 9:50 to 10, this is 80 minutes to 90 minutes. Okay, so this is the sum of 3 properties according to the interval of 10 minutes. So we know that for the uniform distributions, the property of X belong to any interval with the same length. Hence, they have the same probabilities. Okay, so each interval here we have 10 minutes. So the probabilities will be 10 minutes. This is the length of the interval. Multiply by the probabilities is, We have 3 intervals, so 3 multiply each of them, the length of the interval is 10. Over b minus a is 4 over 9. So we have 1 over 3. Okay, this is the way how to apply the uniform distributions to answer for these questions. Okay, any questions, everyone? Okay, if no questions, I left you 10 minutes for rec, then we continue to finish it. Okay, 10 minutes for rec, then we continue with the new distributions. We will return at 1:40. Okay, let's return to the slides. Just one more distributions. Okay. The next continuous distributions we're going to learn together is exponential distributions. Look at the definitions. A random variable t, where t always positive, has the exponential distributions denoted by e lambda. If its probability distributions is ft equals to lambda e power minus t, t greater than 0, where lambda indicates the average number of events per unit length, and t is the number of unit lengths until the next event occurs. So look at these definitions. Which distributions with other distributions we already learned together? We thinking about. Okay. What is the other distributions in your mind when we look at these distributions? How it's relating to one of the other distributions we already learned together? Okay, which one? Which the other distributions we just learned together? Similar to this definition. Everyone? Are you linking to which interval? Oh, sorry, you're linking to which distributions? And how? Okay, how is relating to distributions? Because of the parameter lambda, right? When we work with the Poisson distributions, the unique parameter in the Poisson distributions is the parameter lambda. Similarly here, lambda still indicates the average number of events per unit length. So you can see that the definitions of lambda in exponential distributions is exactly the same as the definitions of the parameter lambda in the Poisson distributions. It still indicates, it still has the meaning, it still has the same meanings, which is the average number of events per unit. Okay, but in the Poisson, it can be the unit of time or the unit of space. Now, the exponential distributions is only defined for t is the unit of the time, where t always positive because t is the time. Okay. Okay, so how the Poissons and the exponentials that related to each other? Remember that the Poisson distributions is the decreased distributions because it counts the number of events per unit. Whereas the exponentials is the continuous distributions. One distribution is continuous and the other one is decreased distributions, but they are related to each other. Okay, how? Now return to the chat box. Return to the flashboard. If Z indicates the Poisson distribution with parameter lambda, hence the meaning is the number of events per unit. This unit can be the length or it can be the space. Now, if consider the number of events per the unit time. Okay. For example, if we count the number of COVID-19 cases, the number of COVID-19 cases within the interval, within the given interval, for example, within the day, or maybe within a week, okay? So because we count the number of cases, the number of positive cases, hence easily we can count the first event, the second cases, the next cases like this. Then the number of cases will follow the Poisson distributions. Okay. Now, in the other side, if we not only care about the number of cases, we also care about the interval time or the durations between two successive cases. It means that we care about how long from beginning until we get the first cases, how long from the first cases to the second cases, and how long from the second cases to the next cases, and so on. Then the interval time between two successive COVID-19 cases, it will be the exponential distribution. And the parameter lambda in exponential distributions is exactly the same as the parameter lambda in the Poisson distributions. Okay, it's really interesting. So remember that if we count the number of events per unit, hence this is the Poisson distributions. If we don't care about the number of events, we care about the durations or the time between two successive events, the interval time between two successive events, from beginning until the first to the second to the third, and so on. As long as not you care about the time, the duration time between two successive events, this is the exponential distributions. Moreover, the exponential distributions has the same parameter lambda as in the Poisson distributions. They are sharing the same parameter lambda, okay? And lambda always indicates the number of events per unit, okay? That's the relationship between the Poisson and exponential. That's the reason why when we have the exercise, usually you are given the exercise, you are given the Poisson and the exponentials the same in one questions. Okay. And here, this is the cumulative distributions of the exponentials. We have ft equals to the property of t less or equals to t. Generally, this is the definitions of the cumulative distributions. Now, for exponential with parameter lambda, ft equals to 1 minus e power minus lambda t, of course, for any t greater than 0. Okay. This is really useful formula. We use this many times. And in exponential distributions, the mean equals to 1 over lambda. This means that the average time between two successive events is exactly equals to the inverse of the average number of events per unit. Okay, and the variance equals to 1 over lambda squared. Okay, this means that in the exponential distributions, the mean is exactly equals to the standard deviations and equals to 1 over lambda. Okay. The same when you work with the exponential distributions, you also need to care. You need to be very careful with the units you are using, because using different units, you have different values of lambda. Okay. Now please practice with example 14. 5 minutes for you. 14. Sorry, this is the mistake. What is the property that there are? Okay, no number 3 here. Okay, there are no loss on in the interval of 6 minutes. Exercise 5 minutes for you. Then please show me your answer in the chat box. Okay, and the answer? Question 1 and question 2. One and two, everyone. I'm waiting for your answers. Any answers? Okay. Go to the board. So in a large corporate computer network, User lock-ons to the system can be modeled as the Poisson process with the mean of 20 lock-ons per hour. This means that averagely for 1 hour, there are 25 lock-ons. Okay, and it's already said that the number of lock-ons to this network is following Poisson distributions. Okay, process is mean that every hour is still be the same. The first hour, the second hour, the next hour is still be the Poisson distributions with 25 lock-ons. So question 1, what is the property that there are no lock-ons in the interval of 6 minutes? So as I told you that always when you work with the Poisson or you work with the exponentials, you still need to pay attention for the unit you are using. Okay. I will answer for these questions using two approaches. The first one just use the Poisson distributions, and the second one using the exponential distributions. Because as we just learned together that the exponentials and the Poissons, they're related to each other. Okay, so in some case, we can answer for the question using both of them. Okay. So question 1. Okay, firstly, let S indicate the number of lock-ons in the unit of the number of lock-ons in the unit of our 1 hour. Okay, and as follow Poisson distribution with lambda equals to 25. Okay. So now, question 1. There's no lock-on on the interval of 6 minutes. Okay. It means that because S indicates the number of lock-ons per 1 hour. But now we need no lock-ons. It means S equals to 0. Okay, the number of lock-ons is 0. But now the interval is 6 minutes, not 1 hour. So we rewrite lambda equals to 6 minutes is 6 over 60 multiplied 25. Okay, so we have 1 over 10, so 2/5. Okay. So now we need the property of no lock-ons. It means S equals to 0. Equals to e power minus lambda power k. Power k is power 0 over the factor of 0. So we have e power minus 2/5. Okay. This is the first approach. How about if we use the exponential distributions? It said that no lock-ons in the interval of 6 minutes. It means that from beginning until 6 minutes, this is the interval of 6 minutes. You have no lock-ons. Okay. If there's no lock-on within this interval, it means that the first lock-ons will be recognized after 6 minutes. This is the first lock-on, surely. Okay. Because no lock-ons within 6 minutes. It means that the first one will be after 6 minutes, surely. Okay, so the time until you get the first lock-on is the interval. It is the interval time. This is the T. Okay, so if we denote T will be the time, the interval time in the unit of hour, because here beginning we are given in the unit of hour. The time between two successive lock-ons, two successive events, two successive lock-ons. It means that from the first one until you get the first lock-on, or the first lock-on to the second lock-ons, or the second lock-on to the third lock-ons, it still be the time T. Okay, it still be the random variable T. And according to our knowledge, we just learned together, T also follow exponential distributions with lambda exactly equals to lambda in Poisson, which is 25. Okay. Now, because we know that T much after T is much greater than 6 minutes, right? The first log on must be approached after 6 minutes. It means naturally no log-ons within this interval equivalent to find the probability of T greater than 6 minutes. 6 minutes is 6 over 60 hours. Okay, 6 over 60 in the unit of 1 hour. So the probability of T greater than something, it will be 1 minus the probability of T less than or equal to 6 over 60. The probability of T less or equal to T0, it will be Ft. Okay, F of 6 over 60. F of T0, where T follow the exponentials, it will be, we use the formula 1 minus e power minus lambda t. So minus 25 multiplied 6 over 60. So it's exactly e power minus 255. Okay. So in question 1, I'm using both of two approaches. The first one using the Poisson distributions, and the second one using exponential distributions. And you can see that we still get the same answer. Okay. Is it clear for you, everyone? Question 1. Any questions? Question 1, everyone, are you following me? Is it clear? Everyone? Why no one answer me? Are you following the lessons? Okay. Okay, so what is question 2? What is the probability that the time until next on is between 2 to 3 minutes? The time until the next log on is exactly the random variable t we already defined here. So question B is very easy. Question B. The probability that the time until log on, the time is t. Between 2 minutes is 2 over 60. And 3 minutes is 3 over 60. Okay, so we have f of 3 over 60 minus f of 2 over 60. And using the cumulative distributions of exponentials, we have 1 minus, the first term is 1 minus e power minus lambda, lambda is 25, multiply t, t is 3 over 60, minus the second term, 1 minus e power minus 25 multiply 3 over 60. Okay, done. We get the answer. Very easy. Okay. This is a very good example to show you about relationship between the exponentials and the Poisson. Is this okay? So next question C. Determine the interval term such that the probability that no log-ons occur in this interval is 0, is 0.9. It will similar to question 1. Question 1, we are given that within the interval of 6 minutes, find the probability of no log-ons. Now, in the different way, we need to find the interval term such that the probability of no log-ons will be 0.9. We are given the probability of no log-ons is 0.9. We're looking for the term. In question 1, we are given the term. We're looking for the probability of no log-ons. Okay, so they are somehow related to each other. It's just different way of asking. Okay, So I will answer for this question using the exponential. Okay, even you use exponential or using the Poisson, it still be the same because it's similar to question 1. So question 3, we're looking for, it means that we find the time t0 in the unit of hour, because at beginning we're given in units of hour, such that no log on within this interval. It means that the probability of t greater than t0. No log on within this interval. It means the probability of t greater than 0 exactly equals to 0.9. Okay. Hence, the probability of t greater than t0 will be 1 minus f of t0 equals to 0.9. Equivalently, f of t0 will be 1 minus e power minus t0 lambda. So 1 and minus 1. So we have only e power minus lambda is 25 t0 equals to 0.9. Hence, we have t0 equals to minus log of 0.9 over 25. Okay, and the unit is hour. Is it okay? Clear for you, everyone? Can you do it by yourself? Is it okay, everyone? If it is not clear for you, so you can stop me. Okay, if nothing, you continue to finish it. Number 4, find the mean term until the next log on. And number 5, find the standard definitions of the term until next log on. So easy. The mean and the variance of t. So we have 4. The mean is mean e of t. E of t equals to 1 over lambda, so 1 over 25. The unit is hour. Remember about the unit. Similarly, V of t equals to 1 over lambda square. Hence, the standard deviation sigma t equals to 1 over lambda. So it still be 1 over 25 hour. Okay, that's all. So we finish this example. This is clear for you about the exponentials. Okay. If no questions, I will return to the slides. Example 15. Again, few minutes for you. Three minutes for you. Read the example and give me your answer in the chat box. Okay. Now, let's estimate the time between detections of the particle with the usual counter and assume that S has the exponential distribution with the mean is 144 minutes. What is the probability that we detect a particular, the particle within 30 seconds of the starting of the counter? Go to the broth. Okay. So we already given that S follow exponential with lambda with the mean is 144, hence lambda equals to 1 over the mean. Okay, remember that E of S equals to 1 over lambda, hence lambda equals to 1 over mean. So lambda equals to 1 over 144. Okay, it means here we have lambda equals to 10 over 14. 10 over 14, so we have 5 over 7. Okay, in the units of minutes. Okay, in the units of minutes. Question A. What is the probability that we detect the particle within 30 seconds of starting the counter? So it's just the normal probability. Okay, we need the probability of S within, it means less than 30 seconds, so 30 over 60. Okay, we change the unit to the minutes. Okay, so it's equals to F of 0.5. F of 0.5 is 1 minus e power minus lambda is 5 over 7 multiply 0.5. Okay, so we have 1 minus e power minus 5 over 14. 5 over 14. Okay, so we have that. Okay, question B. Suppose that we turn on the counter and wait 3 minutes without detecting the particle. What is the probability that a particle is detected within the next 30 seconds? Within the next 30 seconds. So question B. Within the next 30 seconds, given that the counter already turned on 3 minutes without any detections. Okay, so how different between question A and question B? Question B said that we just turn on the counter and start to detect the particle immediately after starting the counter. But now we wait 3 minutes without any detections. It means that we know within the first 3 minutes there are no detections. Okay, there are no any particle detected because we haven't yet we haven't yet starting to detect the particle. Of course, there are no particle found within these 3 minutes. Okay, so actually question A is the normal probability, but question B will be the conditional probability. Okay, so I will write this in the probability of S. We want to find the particle within the next 30 seconds, given that no particle found within the first 3 minutes. It means that surely S must be greater than 3 minutes. Okay, because S will be the term until you get the first particle. And it said that within the first 3 minutes, there are no particle found. Okay, so S must greater than 3. Moreover, we want to find the particle within the next 30 seconds, so it's less than 345. Okay, agree? Hence, using the conditional probability formula, we have the probability of S greater than 3 and less than 3 for 5 over the probability of S greater than 3. Now, the numerator, we have F of 3 for 5 minus F of 3 over 1 minus F of 3. Okay, agree? Now, each of them, we write F of 3 for 5 will be 1 minus e power minus 3 for 5 multiply lambda. Lambda is 5 over 7. Minus 1 minus e power minus 3 multiply 5 over 7 over the denominator will be 1 and then minus 1. So we have only e power minus 3 multiply 5 over 7. Okay. Now simplify these solutions. 1 minus 1, we have 0. Minus and minus, so we have plus. So we reduce this term and this term, we have 1. Minus e minus 3 multiply 5 over 7 divided by, 3 for 5. Here, this is the first term here. 3 for 5 multiply 5 over 7 over by e power minus 3 multiply 5 over 7. Okay, so we have 1 minus e power 3 for 5 minus 3, we have 0 for 5. So minus 5 over 14. Okay, so you have the same answer as question A. Alright. So what is the meaning of this example? Why I give you question A and question B, and then we get the same answer? Can you recognize? In question A, we have the unconditional probability. But in question B, we have the conditional probability. But we still get the same answer. What is the reason? Return to the questions. It said that we turn on the counter and start to detect the particle directly, immediately. Or even you wait after 3 minutes without any detections. And then the probability to get the particle in the next 30 seconds is still be the same as you starting to detect the counter or the particle at from beginning. And then you get the next particle within the 30 seconds, it still be the same. Because here you still use the same 30 seconds. Even at beginning, or even you wait after 3 minutes, the probability still be the same. Okay, what's the meaning here? The meaning is that the exponential distributions, it doesn't remember where you started, right? According to this example, the counter, it doesn't remember that it's already started 3 minutes ago. It just cares that the probability to get the next particle within the next 30 seconds, the interval we are considering will be 30 seconds. Okay, fine. Any questions? I see that you raise your hand. Fine. Okay. So the meaning in this example, it tells us that when x indicates the exponential distributions, it doesn't remember where it started. It only cares about the next interval you are considering. Okay. This really important properties of the exponential. This is called the memory list. The memory list, it means that don't remember about the past. It's only care about the future. Okay. Okay, so to finish these distributions, we derive to the important properties, the memory list of exponentials. It said that if h follow exponential with parameter lambda, hence the probability that S less than T0 plus T1, given that S is started from T0, it still be the same as the probability that S less than T1. Okay, here look at the diagram. Given that S started from S0, here, S0, T0, S is started from T0, the probability to get S within the next interval is T0 plus T1. The length of this interval here is T1. It still be the same as the property of S started from beginning within the interval of T1. Okay, as long as that this interval and this interval is still be T1 and T1. So starting from 0 or starting from T0, it still be the same. Okay, that's the reason why it said that the exponentials is memoryless. Memoryless. It doesn't remember about the past. It doesn't remember where it started. The conditional probability is the same as unconditional probability. Okay. Similarly, the probability of S greater than T0 plus T1, given that S already greater than T0, is still equals to the probability of S greater than T1. Okay, this is the useful properties of exponential. Is it clear for you, everyone, about the lessons? Do you have any questions? Any questions? Okay, so if no questions, we will stop here. We will see you together in the next class, and we will finish this chapter within the next lessons. I only upload the slides, and here you should make the notes by yourself during the lessons. Of course, we need to learn about the normal distributions. This is one of the most important distributions. And we will learn this, we will finish it within the next lessons. Okay, we almost done. We almost finished this chapter. We only have the normal distributions and the central limit theorem. We will to finish it within the next lesson. Okay. No hypergeometrics. We only have Bernoulli, binomial, Poisson's, uniform, exponential, normal distributions, and central limit theorem. That's all. Is this okay? Any more questions? No? Okay, so no more questions, so we can stop here. See you next week.